production. And first is like if you study with me since last semester, you will see that probably first line I will talk about definition, because you should know. I think of you. I am pretty sure that you heard about FEM before, and I think most of you already use it. I believe you use FEM to solve problems, and maybe some of you it's really good in doing this using program, right? That's really good. That's fine. Okay, but I'd like to give you some definition about it. Okay, of course, because before you learn something, you should know what it is. Okay, so I like to give you a very general definition of FEM. Okay, so basically, it is numerical procedure. It is a numerical procedure. Okay, for solving field problems. So it is a numerical procedure for solving field problems. That means, so what is supposed to mean? Okay, it means that, okay, if you have problems like a few problems, you can use finite element method to solve, and it will give you numerical solutions. It will give you numerical solutions. Okay, so this is what this method do. Okay, in general. Okay, so what is a field problems? It can be a problem in, I would say, in like in engineering. It can be a problem in civil engineering. It can be a problem in mechanical engineering. It can be a problem in, electrical engineering. For example, if you talk about the problems in civil engineering, you talk about, structures. You want to design structures. You want to give the section, to the structure. You have structures, and you have to solve the problem. You need to know internal force and all those things. You can use FEM to do it. Okay, or if you talk about mechanical engineering, you want to solve problem in heat transfer or fluid mechanics. Okay, you can also use finite element method to give you a solutions. Even problems in electrical engineering. Okay, if you have field equations, you have equations. Whatever equation is, I don't care. For example, most probably it would be differential equations. So if you have that one, okay, you can solve that problems in electrical engineering, mechanical engineering, material engineering, civil engineering, whatever, using this method. And it will give you numerical solutions because it is numerical procedures. Okay, so this is what FEM do. So if you know this, you will see that the package, FEM package, that very commonly known to engineers around the world, like what ANSYS, Abacus, or SAP, or all those things. Especially ANSYS and Abacus, you can use by any field of engineer to solve for their problems. Okay, but in our case, I think since we are in civil engineering, so normally problem that we will focus on would be what we call quantum mechanics problems. It would be quantum mechanics problems. Okay, so what is quantum mechanics problem? Those who already passed advanced makeup maths. Okay, because I wrote this out again. Okay, you should know what would be the quantum mechanics problem, especially if you already pass the Attention part already. So you should will understand that one. Okay. So, but anyway, I will just copy the definition from that course and put it here again. So it is a study. So quantum mechanics problem is the study of mechanical behavior of a body, solid or fluid. Solid or fluid. Even though in our case, it would focus on only solid. Okay. So it's study of mechanical behavior of a solid body, let me say that, under the action of forces on the macroscopic scale. So the keyword is here, okay, macroscopic scale. So it ignores discrete nature of matters and treat materials as uniformly distributed throughout region of spaces to be able to define field quantities, okay, like density, displacement, velocity, etc., as continuous function of position and time. Okay, those who study this course probably see this before anyway. Okay, so I explained this since this course. So this is what we're gonna learn. Okay, in here basically. So we focus on a solid body on the macroscopic scale. Okay, for example, if we study the concrete, we know that concrete consists of if you study concrete, right, you would have aggregate, cement paste, and all those things, right? Mortar like this, right? So it's basically it's not homogeneous, but in macroscopic scale, we just think they just any point in this domain, okay, you know, on the macroscopic scale. Okay, so you can define the quantities at any point in the domain. We don't care if you point here, you see aggregate. In here, you see mortar, no. So if you separate the concrete into different phases, then we talk about microscopic scale, micro scale. Okay, so and that would require, you know, more advanced theory to understand that. But in here, we just consider only the macroscopic scale. So like this, okay. So what we're gonna learn here is an element method for the problems like this. Okay. So what shall we do, or what can we do with quantum mechanics problems? Okay. So if you have the problem that you want to solve, you model, and then become that model, because the problem would be given by mathematical equations. So mathematical model is actually is math equations, right? Mathematical equations, and that equations normally consist of conic equations and boundary conditions. Altogether, they call boundary value problems. Okay, you already see this also in the previous course. You know, so basically, you want to solve quantum mechanics problem, you end up solving mathematical problems or mathematical equations, which consist of equations and boundary conditions. Okay, okay. For example, you want to solve beam. Okay, one beam. Okay, this is probably the simplest problem that I can think of. You have a beam. Okay, and beam like this. So what you need to do is model. So then you can model, John, I can model beam as a single line like this with boundary conditions like this. So if you solve this one, subject and also subject to certain loading like this. So this is boundary value problem. You must have conic equations or beam equations and also give boundary conditions. Okay, so you can solve this one. You end up solving mathematical equations. Now, for the previous, let's see this one. Okay, for the previous course, like 2101607, normally what you like to find the equations you solve using analytical methods. Okay, any methods that you can solve those equations analytically. That means when you have equation, you can solve it using mathematical procedure. It becomes analytical solution we call analytical methods. That's okay. You get the solution that we call analytical solutions. So whatever you want to use, separation of variables, okay, integral transform, or whatever that you learned before. Okay, so that's okay. But this is like an analytical part. But in this course, we will focus on this, what we call numerical methods. And in particular, this method, FEM. Okay, because in this problem, like a continuous mechanic problem, okay, if you can solve it using analytical methods, so that's okay, you can solve this one. But in some case, analytical methods is not possible for certain problems. So then you may require numerical methods like this. And this is the focus of this course, and in particular, this method FEM. And for numerical methods, one of the keyword is we call discretization. Discretization. So normally numerical methods, come with discretizations. Okay, come with discretizations. Okay, so this is our focus of our study. I just give you some basic idea about the numerical method discretization. Look at this one. You have a circle. So this is a circle. I have a circle. And this circle have a radius r. Okay, radius r. So we all know that perimeter, I think we all know that, right? Perimeter would be equal to 2 pi r. 2 pi r here. This is what we know since, I don't know, elementary, like grade, elementary school, right? We know this equations when we study geometry, right? Now, if we divide the area of this circle, or divide this circle into polygon of n size, okay, for example, like this, we have polygon of s size here. We divide the area like this, and this one become the polygon of n size. Okay, even though this is equal to 8, but you can divide it more or less than this 8. So basically, in general, we have polygon of n size. And then for each angular here, the radius, this radius still r, right? And the angle here would be 2 pi over n, depending on the number of size that you make. In this case, if you look at this picture, this is 8, so this would be 2 pi over 8, something like that. Okay. So anyway, from this, you can find the length here. Okay, would be equal to 2r times psi pi over n here, right? So then if you want to find the total length of this, straight line here, it would be equal to what? 2 pi, let me see, it should be n times 2r psi pi over n, right? The total length here, right? It would be equal to n times 2 psi pi over n. And this is here, and this is the perimeter of this discretized circle. Okay, so what I'm trying to do this is to show you, okay, the basic idea of discretization and numerical methods here. Okay, so if you compare this and this, okay, so this is the actual, let me see here, okay, the actual perimeter of the circle, and this is the perimeter of the circle if you discretize into polygon of n size here. Okay, you compare these two. You have 2r here, 2r here. So you can say that pi n. What is pi n? So if you compare, maybe I should see that's equal to, let's say this is 2 pi n times r. Okay. Okay. So when you compare pi n here and the term here, you will see that pi n would be equal to n sine pi over n. Okay. So what I'm going to show you is if you increase number of n, that means you discretize this circle using more, more triangular area here, or increase the size of this polygon. Pi n should approach pi. Okay, pi n should approach pi. So what we do here is I just compute when you use n equal to 1, 2, 3, 4, 5, 6, 7, and what increase number, and pi, this should be pi n actually, and this is pi, exact pi, 3, 1, 4, 1, 5, 9 something. Okay, so it means that when you use more term here, function pi n here should approach the exact pi. So this is the nature of numerical approximations or numerical methods that we expect. So that is, it involves approximation. Okay, so you need to do some discretization, and then when you discretize using more elements or more terms, you should expect the solution approach the exact one or the exact solution. Okay, this is just some basic example that show you that what we expect. Okay. Okay, and this is the nature of approximate method. Okay, and so you may ask me, John, which is of course you should ask actually, why we need to do that? Why we need to do this? Since we know that perimeter of the circle is always 2 pi r. Of course, that's true. You don't need this. You don't need to go all this trouble to to compute like a polygon, the perimeter of circle like this. Of course you don't. But in some case, you may need to perform numerical methods because because it's not possible to go this way to get the solution you want. So then you may require to go this way. Okay, you may require to go this way. Let me just give you, probably the last slide for today. You just look at this beam. Okay, let's say we have a beam. Okay, a beam, cantilever beam, cantilever beam, subject to point load P here. And if you want stress or deflection of this beam, what shall we do? We do analytical methods or numerical methods. Actually, the answer would be we can go either way. You can use numerical methods or you can use analytical methods. Okay, depends. But if I want to find, okay, stress around this hole, for example, the accurate stress around this hole, accurate stress around this hole, the distribution of stress, we know from the stress, the fractional stress due to the beam, right? MYOI or MCOI, okay? That would be, possible if your beam is, of course, thin enough. But if this is really thick compared to the length, okay, we have to think about the accurate of this formula also. So in this case, if you want to find accurate stress, maybe the classical beam solution is not, of course, it will give you certain solution, but is it accurate enough? I don't know, especially if you want to find what would be the deflection here, the tip deflection, right? Okay, it depends on what you want. If you want just approximate solution, maybe it's okay. You can get roughly what would it be. But if you want the really accurate one, maybe it would be a good idea to try to use numerical method, especially FEM to solve this problem. Okay. So this is maybe one example to show you that numerical methods is more appropriate to this one if you want really quite accurate results. Okay, and I think I don't want to go into much detail today. This is the first day. So I think it just introduce the subject is enough. I think next week I can finish this one, of course, because just so show you some overview of the course, and then we can go into the first topic of Bell excipients method, which I think you learned something about it already. Okay, so we can discuss more next week. Okay, so right now I think it's gonna be I'm gonna stop talking today right now. So any questions if you want to ask me ครับมีคำถามอะไร